And I'll just go on YouTube and make sure that the everything sounds good and looks good.
Yeah. Well, I guess so. That's where the fabric. So I guess Google has really good fabric, so you never have to click on this. You just send it and square it and it just works. So I don't know what fabric is yeah. Because most people would be here, like people roll in. Yeah.
We'll give people like another minute or so to roll in. Oh, and by the way.
Yeah, so that's just another one.
So, once you plug it in, it wasn't work.
Okay. But is there any, I mean, assuming you have this pattern, is there an advantage of that structure?
It's just very simple. You can always just have problem with that, or just this is not you don't have to think about when you go back to that chart or that chart. So it's engineering separate. Yeah, with the segregation, you have to think about the level clarification.
Yeah, sure.
Maybe not to 21. Okay.
That was actually.
There was.
Right, so it was actually. One responsible for activating and doing their slicing. A lot more.
Well, the first one.
Did you?
We'll just say they probably more people are going to
Oh yeah, perfect. Yeah. Oh, there's actually. Do you want to? I mean, just for the event, so you can speak and feel free to write questions. Oh, there's actually. Do you want to? I mean, just for the event, so you can speak and feel free to write. Can you say something just so that I can make sure that everything sounds good? I just want to. Yeah, like a test.
I think I did turn the mic
Can you
off.
say something just so that I can make sure that everything sounds good? It's like a little bit of a delay. Sorry.
Oh, is it?
Like test.
Let me turn my mic on.
Yeah. No.
Yeah.
Better?
You need to turn your mic on.
I did turn it on.
It's like a little bit of a delay.
Just turn it on.
Okay, just that's why. Let's do this one more time.
Test.
Yeah, I hear it. I heard it on my fantastic. Let's do this one more time. Yeah. Okay. Do you mind? Sorry, there's like a lot of confusion. I said everybody's in the mobile space. Okay, thank you so much for being so accommodating. Yes, absolutely. Sorry, there's a lot of people do have questions.
Let's keep it that way.
Yes, but it's back. Are there people in meetup saying that they're dazed and confused? Other people? I don't see anybody coming, but we'll wait another minute. We're a lot more situated at the USF because we've been doing all the events there. I don't know what. It's pretty steady. Let's see. Maybe it's gonna touch. No, it's perfect. Look at that. Oh, there's one. All right. Well, it is. All right. Yeah, I think we should start. Yes, it is. I guess let's start and see what we can start. Yes, it is. Let's see. So this is our second to last meeting, and it's the only one that's not at USF. So next one is going to be at our usual spot. So that's good. What was I going to say? We're still going to go out afterwards, just not to our usual spot. So if anybody knows of good places around here, we'll go there. And yeah, I think that's all I got. Sorry for being a little late, and I'll give it to Rajhans.
Right, cool. So this is chapter 16 of the book. This is also my first time coming to this meetup, so I'm not quite sure of the format, but I would assume that you can just interject me, ask any questions or whatever. So just a heads up, there is very little deep learning in this chapter. it actually deals with a fairly sort of classical machine learning topic called graphical models, which is a huge topic in its own sort of right, and used to have like 2 or 3 different tracks at NIPS. So I mean, it's kind of a big topic to cover in one chapter and one sort of like, discussion. But I mean, I've tried to sort of give some sort of an idea of this, being fairly faithful to the book. Let's see how that goes. Anyway, so my name is Rajhans. I am chief data scientist at a startup called Spoke. Before that, I was a research scientist at Google doing NLP and machine learning. I will give us just a small shameless plug of Spoke. What Spoke is it's a smart and simple way of managing requests inside a company, sort of like a smart ticketing system, if you will. And it uses machine learning and natural language processing to like automatically answer questions people have. And it's built for multiple teams, so it can assign requests to right teams. It's much easier to use and uses AI to actually make your life easier, as easy as possible, basically. And we are hiring in machine learning, so in case anyone is interested. Cool. So here is an outline for this talk. I will give sort of a motivation of graphical models. Then I will talk about a certain kind of graphical models called Bayesian networks. Then another kind of graphical models called Markov random fields, which are the undirected graphical models. Then we'll talk about different things like separation, which is what does it mean for 2 variables to be independent given a graph. Conversion between different kinds of graphical models. We'll talk about inference and what inference means. And then we'll talk about the deep learning part of graphical models, specifically restricted Boltzmann machines. And then if time permits, I would like to talk about stuff that is actually not in the book. This is what is called discriminative models, and we'll talk about it. Discriminative is not used in any offensive sense here. Cool. So some of these slides I have borrowed from Eric Shing's course in CMU. At CMU. And then a few days ago, I contacted Ian Goodfellow, who was gracious enough to upload his latest slides for graphical models just in time. So I did use some of those, but I did find that his slides were not as complete as I would like to be. So I added more slides to it. So in general, so what is graphical models? So in general, like what's the problem that we are trying to solve? Let's assume that you have m number of variables, right? And it could be variables from some social network or some sort of gene expression data or whatever, right? And you want to express some sort of a probability distribution over different settings these variables could take, right? And a graphical model is actually a really cool way of doing this. Okay, so to give you some, I mean, basically to describe what I just said, if let's say you describe the world around you using different variables, right? So like, is it going to rain tomorrow, or is it going to be smoggy tomorrow? What is my commute time going to look like, right? All of these are sort of different variables that are not necessarily independent of each other and that describe the world state, right? And you want to capture sort of uncertainty in these variables, and you want to capture sort of dependencies between these variables so that you can make meaningful predictions about the world, right? So the fundamental questions graphical models try to answer is that how do you encode dependencies between these variables so that you can best possible answer such questions? And then you want to make you want to make queries like the inference query. So what an inference query is, given some data, what is the probability of my commute time being greater than 30 minutes tomorrow, right? So given n number of variables that you have, what if I want to answer a question about a particular variable? So that's one of the inference problems. And then the learning problem is, given a whole bunch of data, how do you learn the parameters of this model, right? So each of the models is expressed by a set of parameters, and how do you learn it? So just a quick recap of basic probability. Let's say you have 8 binary variables, right? And you want to describe a probability distribution over these variables, right? So normally you would have 2 to the 8 different configurations, right? You would have a big table which would have all possible 8 configuration, and you would assign probabilities to each of them, right? So and you can get these probabilities using maximum likelihood, etc., etc. There's a whole bunch of like tools in statistics that deal with this, right? And so basically what graphical models, let me actually skip ahead a little bit, is that let's assume that the certain variables are independent of other variables given a subset of some of the variables, right? So in other words, you could potentially, what if I told you that instead of 2 to the 8 different possible parameters in your distribution, you could represent a probability distribution over these by something like 36 different probability distribution, right? So in other words, and actually let me skip ahead a little bit and I'll come back to it. This is sort of what a Bayesian network looks like, right? So in some sense, this describes which variables are dependent on which of the other variables, right? So it's, in some sense, it's saying that x1 and x2 are independent of each other, right? And that x4 is only dependent on x2, right? So we will make it more formal, but the general idea is that what you're saying here is that the probability that x3, let's say this is some gene that is expressing itself, will express or not is only dependent on whether x1 expresses itself or not, right? So what we are, in other words, what we are saying is that x3 is independent of every other variable, right? So this means that to describe the probability distribution, let's say you want to describe the probability distribution of x6, right? So then you only need to describe the probability when different values of x3, for different values of x3 and x4, right? Because x6 is independent of everything else. Does that make sense? So in this case, what is the size of the probability table that would describe the probabilities x6 could take, right? So x1 and x3 and x4 could take 4 different values because they're just 2 variables, right? And for each of those 4 values, x6 could also take just 2 values, 0 or 1, right? So the size of the table that would describe the probability of x6 occurring in different possible states is just 8, right? So now you can similarly sum up the conditional probability of each of these variables given its parents, or parents in the graph. By parents, I just mean nodes that are upstream that are directly related to it. And basically that size comes out to be whatever 2 plus 4 plus 4 plus 8, whatever, 36, which is much less than 2 to the 8, which is 256, right? So we'll make this notion more precise, but the general sort of cell here is that you are using graphical models to do multivariate statistics or statistics over multiple variables, but you're using it to impose a certain structure on these variables, right? So which is a little bit different from a lot of deep learning frameworks where you kind of go fully connected between different things, right? And then you expect your training algorithm to discover these things. In graphical models, typically you really want a sparse structure that you can understand and interpret, right? Does that make sense? Any questions? So we will go into more details of this, but basically the sort of an informal description of designing graphical models is that you encode the probability distribution over a bunch of variables using a structure which is a graph, which allows you to do it in a very succinct way. And it allows you to capture certain dependencies in a way that is very meaningful, and it allows and is scrutable, right? So anyone can sort of look at this graph and say, does it make sense or does it not make sense? Or someone with a domain knowledge can come and actually design a graph for your domain, which can actually be used to encode all possible dependencies. So yeah.
So you'll never learn the graph.
You can learn the graph as well. You can learn the graph as well. So traditionally, I guess like mid 80s, early 90s. So Judea Pearl, who wrote the book on what is called graphical models or something, he won the Turing Award for that, and he describes uses graphs to express causal structure between different variables. And in that case, he assumes that the graph is given. You're not learning. But then there's a bunch of work that has happened afterwards, which sort of allows you to, given a data, come up with a graph that is the sort of, in some sense, like the minimal possible graph that can explain the data by, it's sort of like some sort of Occam's razor-like argument. But yeah, you do learn the graph as well. So there are multiple applications of graphical models in machine learning and in statistics. It's used in computer vision, used in natural language processing, robotics, information retrieval, all sorts of stuff. In general, this is sort of a very common language that a lot of statisticians want to use, because this is it's a very precise language, and you can use a bunch of stuff from graph theory to prove a lot of properties of this model. So there are two types of graphical models. One is the directed graphical model. Yeah.
How big can this graph be?
As big as your data. So this is, I mean, it depends. Again, early days, 90s or whatever, people were designing graphs, so they were like 500 or 600 at the most. But then I think a bunch of people have actually been creating like really big graphs. The problem with big graphs is the inference becomes really complicated and becomes really hard. But then now people are coming up with these variational techniques that allow you to sort of do inference over, hundreds of thousands of variables. So, which is, I mean, so now people are designing big graphs. Max Welling, I know, has been doing some of this stuff as well. So he's also does a lot of autoencoder and variational autoencoder stuff. He also does. He's also pretty well known in sort of graphical models community. Yeah. So two kinds of graphical models. One is directed graphical model, and another is undirected graphical model. So the directed graphical models are actually easier to understand, I think, because we can sort of assign semantics of causality to them. So basically, again, the undirected graphical model assumes that the probability over 8 variables, each of these 8 variables, factors based on this graph, right? So let's actually go do this exercise. So x1 and x2 have no parents, right? So their factors are just px1 and px2. There is really no conditional probability in that, right? Then x3, the parent of x3 is x1, right? So you define the probability as x3 given x1, because the parent of x3 is x1, right? And parent of x4 is x2, so again x4 given x2, x5 given x2, and then for this is I think x6, so we write down this is probability of x6 given x3 and x4, and so on and so forth, right? So in some sense, this is like simplified chain rule. If you really want to, let's say there were no independence assumptions like this, so you could always write the probability of each of these variables. If none of this was true, then you can write it as p of x1 times p of x2 given x1 times p of x3 given x1 x2 times p of x4 given x1 x2 x3 and so on, right? So that holds true regardless of any kind of independence assumption. So this is in some sense sort of breaking it down and making it much simpler, right? So in the original case, we had exponential number of parameters, right? In this case, we have a much smaller number of parameters. That's sort of the beauty of graphical models, that allows you to express fairly rich dependencies between different variables, but with much smaller number of parameters. And then undirected graphical models, they're not giving causal links between variables. They're only expressing correlations between variables. And we will come back to it and try to understand what it actually means. Okay. So Bayesian networks, I guess that's the first ones. So what is the meaning of a Bayesian network? So a Bayesian network is always given by a directed acyclic graph. You can't have cycles in the graph. Otherwise, the independence assumption sort of breaks, right? You can't have x depending on y and then y also depending on x. So the semantics is that a node is conditionally independent of every other node in the graph given its parents. So basically, to actually know what it means is to know the probability distribution of a node, you only need to know what are the values of the parents of that node. Does that make sense? I mean, so basically, so this node, right? So for instance, if I so child's co-parent, right? So if I want the probability of this node, right, and then I'm given this node, then I don't this node and this node, then I don't need to know the value of any other nodes, right? So in some sense, I think there was a nice example that Ian had in his book where, let's say there are 3 runners who are running, right, and each of the runners, they're running sort of a relay race, right? So the runner A runs and gives the baton to runner B, and then the runner B runs and gives baton to runner C, right? Now, let's say you have a probability distribution over the time of finish of runners A, B, and C, right? So now, if I want to predict, have a probability distribution of runner C, then it is independent of the distribution of runner, or independent of the time runner A took, provided I know that how much time runner B took, right? Because the time the runner C would take is only going to be dependent on when B finished. And sorry, we're talking about finishing times, not the total time that took. So in some sense, C is independent of A given B in that case, right? So anyway, so this gives causal relationships, and in some sense, it's what it's really doing is it's giving a generative process, right? This is telling you how your data was generated. So you just generate the nodes that had no parents, right, in the beginning, and then you sample like nodes which are sort of in a topological sort starting from there. So Bayesian network is a directed graph whose nodes represent random variables and edges represent direct influence of one variable over the other, right? And in some sense, it's a nice data structure that provides a way of expressing joint distribution over all the variables in a simple factorized way. It offers a conditional, like compact representation. So like this is an example of a conditional probability table, right? So let's say if this was your Bayesian network, this is how you would describe this network in a complete way. So A and B have no parents, so you would write down the probability of A occurring in state 0 and 1, which is independent of everything else. So let's say it's 0.75, 0.25, so on and so forth for B. Now for C, the probability of C occurring in each of the states depends on what the state of A and B was, right? So the conditional probability table in this case will have 4 columns, right, and 2 rows. So each column corresponds to each possible state in which the parents occur. So if the number of parents of each or of a given node is n, then you would have 2 to the n number of columns, right? And then so it's fairly simple. Does it? I think this should. If this is clear, then I think we should move forward. Otherwise, we can totally discuss.
Yes. Bayesian networks is the same thing. It's a synonym for graphical models.
Yes. Yes. Bayesian networks are
But the book doesn't use the phrase Bayesian network.
Really?
Until much later.
But Bayesian networks are directed. I think you can use synonymously, unless there are some weird edge cases that I can't recall. But I think you can use them synonymously, interchangeably. Yeah. Yeah. Cool. Questions? All right. So one of the famous Bayesian networks, you might have seen this, is a hidden Markov model, which is sort of like a kind of often used for time series analysis or like part of speech tagging and that kind of stuff. So you assume that there is a hidden representation that you don't know that you want to infer from the data, and then conditioned on the hidden variable, you see an observed variable, right? Since let's say, for example, you want to do part of speech tagging, so then the part of speech tags would be hidden, and the words are generated conditioned on the part of speech tag, right? So you get to observe the words, and this is your hidden variable. So oftentimes in this case, the task is to predict y given x, and that's sort of the discriminate. I'm hinting at the discriminative models domain, which we can come back to later. Okay, so what are undirected graphical models? So in undirected graphical models, you don't know any causal links between things, but you still want to express a probability distribution these variables can take, right? So there is no way to explicitly, there is no like explicit generative structure. So actually, let me quickly actually show you what the form of the distribution is, and then we'll go back. So in this case, so in this case, if I give you a graph, which is an undirected graph, then the probability of any configuration these nodes can take is just a product of some functions that are defined on the cliques of that graph, right? So in other words, let's say there is an image like this, right? And often we want to impose constraints on these pixels or sort of nudge them. Let's say you're doing image segmentation. So you want to predict background from foreground, right? So oftentimes you want to impose things like if this pixel is in the foreground, then it's very likely that the neighboring pixels are also in the foreground, right? It's not a hard constraint, but you kind of want to encourage that, right? So what you can do in this case is to just assume that, let's say, these edges are like the cliques in this graph, right? And so this is not maximal cliques, but this is, I mean, this is how I'm assuming it's factorizing, and we'll come back to what it means to actually have cliques in the graph. But let's go with the flow for now, and let's assume that the distribution over all these pixels is going to factorize over individual edges in the graph, right? So then you can say that the probability that these two nodes are in 1, 1 or 0, 0 state is higher than 1, 0 and 0, 1 state. What does that mean? That just means basically if 1 is foreground and 0 is background, then you're encouraging two neighboring pixels to be in the same state, to have a higher probability than for the neighboring pixels to have different states. So given that, let's go back to the definition. So the formal definition of a Markov random field or an undirected graphical model is that each node is conditionally independent of all the other nodes in the graph given its nearest neighbors. So there are no parents in this case. There are just the nearest neighbors, the nodes that are directly connected to it, right? And basically the beauty of so this is what is called the local Markov assumption, which is that each node is independent of everything else given its local, what is called the local Markov blanket, which is the nodes that are directly connected to it. And the beauty of, I mean, and this is like a very nice theorem which sort of shows that if you make this assumption, then you can show that the distribution over the entire set of variables actually factorizes, or basically is a product of some functions that are defined on over the cliques of that graph, right? So let's, I mean, this is, I guess, too much mumbo jumbo. Let's maybe discuss a concrete example. So let's say this is your undirected graph, right? So now you want to write down the probability of A, B, C, and D occurring in different possible states, right? So what you do is first of all you find out, you create cliques in this graph, right? So by creating cliques, I mean basically A, D, and C, they all belong to some sort of, you kind of cliqueify the graph by connecting all the nodes that are in the same, how should I say, in the same neighborhood, but are not connected by a direct edge. So you basically convert the graph into sort of 3 different cliques in this case.
So wait, is it the think like A, B, B, and that's a complete graph, right? So a 3-line cycle, or if you have a full connected graph of length 4, I guess it's
actually no. So you're right. You're right. So I think the notion of cliques here is a little confusing. I guess we'll come back to that. Okay. So let me just there is this thing called factor graphs that solves this confusion. So let's assume right now that the factors here are given only by the edges in this graph, right? So the probability distribution of A, B, C, D occurring in any sort of setup is going to be a probability of which factorizes over these edges, right? So there are what six of these edges, and each of them have 2 terms, 2 edges. So two nodes. So it's just going to be a product of 6 different terms. Each of them is derived from let's sort of like a table which is of size 4, right? So yeah, I mean, this is basically what it says, that we can represent P of x14 as 5 2D tables instead of 1 4D table. So maybe we should do this exercise to make it clearer. But actually, let me quickly talk about factor graphs, which I think will make life much easier before we do any further. So often the representation of an undirected graph gets really ambiguous. So for example, if I gave you a graph like this, A, B, C, right? You might be asking, like, you know, what is it 3 different pairwise potentials, or is the distribution over the entire clique, right? So you could view it as a distribution that is expressed by this edge, and this edge, right? Or you could view it as a distribution that is expressed by all 3 nodes together, right? So this is sort of a confusing notation because it's not unique, right? So to uniquify it, there is this thing which we call a factor graph representation. So let's say assume the original nodes are represented by circles. So then you add these factors which are like square boxes. These are just auxiliary variables that are used for making life simpler. So if you represent it this way, it means that the distribution is expressed by all 3 variables together. So this is a factor that connects all 3 nodes. So in this case, the table that you really need to specify is going to be 2 to the 3 sized, right? Because you have to express all possible ABC variables. But in this case, it's just going to be 2 to the 2 size plus 2 to the 2 plus 2 to the 2 size. Right? So this is sort of an unambiguous way of representing distributions through undirected graphs. So here is what actually maybe the best is to talk about restricted Boltzmann machine. Sorry, I'm just trying to see if what's the easiest way to explain this. Right. So in Markov, so Markov random fields, they come from statistical physics literature, and there people often use what is called energy functions to express the probability that each of the, let's say you're looking at a bunch of particles, what are the different states these particles could exist in, right? And so the way they describe the energy function is often as exponential of minus times some sort of a positive positive function, right? And this is what is called the energy, and this is sort of the probability of it occurring in that particular state. So this is sort of like, if any of you maybe this is like high school physics, but like statistical mechanics describes the probability of each bunch of system of particles occurring in each state as the exponential of negative times the energy of that thing, right? So the higher the energy, the less the chances of something occurring in a particular state are. So this is also what is called a Boltzmann distribution. Yes, so I think this is, any questions about this? I know this is not sufficient to give an idea of MRFs, but we can sort it out and talk it out.
How is this related to the rest of Boltzmann machine?
So in general, that's a good question. So here is the let's say you're given a Markov random field, which is you're given an undirected graph, and you're given that these are the edges or the cliques on which the distribution factorizes, right? So by factorizes, I mean when you want to write down the probability of all n of those variables, then it's a product of probability, a product of some functions over certain subset of variables, right? So this represents, you can think of these C's as cliques, right? But this could be just edges over the graph, or could be just some sort of subset of the nodes at a time, right? So this is a product of, you can think of it, if you want the Bayesian network analogy, in Bayesian networks, it was just a product of probabilities, conditional probabilities, right? In this case, these are not conditional probabilities, these are just some positive functions. And we would convert everything into probabilities by normalizing. So this is the Z variable, which is what is called a partition function. So if you give me any positive function here, right, I can always normalize it and I'll get a reasonable correct probability distribution, right? So in this case, it is a product of positive functions over non-negative functions over subset of variables, right? So now if I make an assumption that the probability is non-zero for all possible states, so the probability is never zero, it can be very low, then actually what I can do is I can write down this psi of x as e to the minus phi, right? Because it's a positive function, so I can always write it as e to the minus phi of some other function, right? So then what that allows you to do is, so this is what I did, right? So I wrote this as e to the minus psi. So then the beauty of that is that now the product of these psi variables has become an exponent of the sum of the phi variables, right? And this is sort of the what is called the free energy. These are all terms from statistical mechanics. I mean, there are machine learning people do work on them, and there are some very nice, like there are conferences that are dedicated to just sort of this kind of analysis.
You just change the variable.
Right.
No,
Yes.
no physics in here.
No physics in here. So actually maybe let's talk about. So the what you can do is now you can say that actually let's go back. So yeah, so now I can say, let's say I don't know the images. I don't know. I want to do segmentation for this image, right? But I'm not given the actual pixel value. I just want to come up with a prior on the possible configuration these pixels can take, right? So to describe the prior, I can use this kind of Markov random field like distribution, right? Because I can always say, let's say I have some sort of domain knowledge, right? So I can say that, as I said, like pixels which are neighboring to each other should all be in the same. It should all be either in the background or should all be either in the foreground, right? So that I can use that to put a prior probability distribution on my data. Right, and then when I actually see the pixel and then I run, let's say maybe I run a deep neural net on that or whatever on top of that, then I can multiply the probability of that with the prior distribution I have, if I want, to get a more reasonable estimate. Right. So in other words, maybe we can talk about this when we discuss discriminative models. But this allows you to express certain things about your data, and without actually having to learn it from scratch. So yeah, so anyway, so the summary here is that Markov random fields, or often expressed as factor graphs, do not make any conditional independence assumptions. They just say that the probability of occurrence of these variables, or probability of these variables taking a certain state, is just going to be a product of probabilities of certain functions defined over small subset of these variables, right? And then if those probabilities are always positive, then it sort of can be exponentiated, and then it leads to a nice form. Basically, that's sort of like the TLDR of this whole thing. So separation. So separation in this this is a slide from Ian. So separation in this case, what does separation mean? So by separation, I mean that two variables are considered separated given a graph if they are independent of each other. So if specifying the value of one does not tell me anything about the value of other, right? So in this case, let's say if I gave you this Markov random field where the distribution is over edges, and if I tell you what the value of S is, then A and B are separated from each other, because I already know what I want to know about B from S. So telling anything about A is not going to help. Okay, so A and B here are conditionally independent given S. So separation in I think in Markov random fields is much easier, because you can just say that if there is no path going from A to B, then A and B are independent. And if any of the nodes are observed, then you sort of just take them out of the graph. So in the resulting graph, if there is a path, then they are not independent. If there is a path, then they're not independent. Yeah. And there is no path, then they're independent. And graph separation in Bayesian networks is slightly more tricky. It's in Bayesian networks, separation is often called deseparation, because directed separation. And so it's a really funny thing, but in order to do separation in Bayesian networks, you convert them in effect into Markov random fields. You convert them into undirected graphs, and then you study separation in them. So there's this really funny term called moralization, and moralization here basically just means that if two nodes have a children without getting married to each other, then you marry them. So you connect sort of a node edge between them, and convert all the nodes into all the directed edges into undirected edges, and then you can answer separation questions from this graph. So I mean, this is just some examples of what are the independencies that you can explain. So if you fix B, then A and C are independent, because the probability of A being in any state is completely expressed by B taking a particular value, right? And similarly, if you have A going to B going to C, and if you know B, then C is completely independent of A, because whatever I needed to know about C from A is already expressed via B, right? But the weird thing is, if A and B are both connecting to C, so in the original graph, A and B were independent. But in the graph, when C is known, now A and B are coupled, because now we know the value of C. So in some sense, they are moralized. You have to connect them, and hence they're not independent in this case. So this is sort of a fun exercise to just like see, given a graph, which nodes are independent or not. It's not as trivial as I initially thought it was, and it took me some time to actually get it. So anyway, deseparation, a whole bunch of stuff. And yeah, needless to say, this is just a trivial point, but a complete graph can represent any probability distribution, because in some sense you're just saying, I don't really know any independence assumptions about this data. You have to express all possible different probability states explicitly, right? I think this point should be fairly obvious. So in some sense, the graphical model's representation is a complete family of distributions, because it can express any distribution. In the worst case, you'll just have to represent it with complete graph, but hopefully not, because life is much harder with a complete graph. Let's skip the conversion between undirected to directed and directed to undirected. From directed to undirected, you just moralize the graph, you get and you remove the directions, and you get an undirected graph. And let's quickly talk about inference. So sampling from directed models is it's pretty easy, because you just do a topological sort of the graph, right? So you first sample the nodes that have no dependencies, and then conditioned on those, you sample the nodes that are at the next level, and then at the next level, and then at the next level, right? So in some sense, it's sort of like doing a breadth first search, right? Sort of, and going in that order. Sampling for undirected models is really hard. It's because there is no sort of ordering of these nodes. So people often use this, what is called Gibbs sampling, where you start with some configuration. So you assign some random values to these nodes. So like 1, 0, 0, 1, 0, whatever, right? And then you sample each node conditioned on by fixing all the other nodes, right? So if I fix all the other nodes, then I have a probability distribution over this node. So I sample from that. Then I do it for other nodes, and I do it for other nodes. And then eventually what happens is that this Gibbs distribution, or this sort of a sampling kind of like a Markov chain, converges to some distribution. And then you can sort of sample from. So inference and approx inference. So inference in this case, so first of all, what does inference mean? So inference in this case mean that given a graph, give me the probability of x2 being 1, right? Or given a graph, give me the probability of x1 being 1 and x3 being 0, given that x4 is 5. x4 is equal to whatever 1. So I mean, to give more concrete examples, let's say you have things like what is the probability of my commute taking more than 30 minutes given that it rained today, right? And then there's a whole bunch of other variables that you kind of have to sum over. So variables like, is it smoggy, what's the sunshine, or is there, I don't know, is it a Monday or is it a Thursday, so on and so forth, right? So you need to basically sum out all the other extraneous variables just to get the probability of what my commute time is going to look like tomorrow, right? So the interesting part is that the inferring, sort of doing this kind of inference, is an extremely hard problem. It's not just NP hard, it's actually short P hard. So short P hard is like worse than NP hard. NP hard is like saying, I mean, I'm assuming NP hard, so most people here know about NP hard, but NP hard is just this class of problems that is extremely hard to solve. It's like saying whether a given circuit is satisfiable or not, whether there is a particular value that you can assign that would allow you to satisfy all some set of constraints. And short P hard is harder than that. It just not only says that you have to answer whether something is satisfiable, but you have to count all possible satisfiable solutions. So anyway, so it's a hard problem, and so people have to rely on approximate inference. There are very many cool algorithms. One is called belief propagation, bunch of message passing algorithm, variational inference techniques. Some of that is shared with the neural net literature, especially like the GAN sort of literature, where and variational autoencoder stuff, where you kind of come up with approximate inference techniques to come up with a distribution over data without actually explicitly or exactly trying to solve it. Yes. So typically in graphical models, this has been done for like 15 years. So there is often lower bounds. So you can prove, for example, that some of these message passing techniques are maximizing a lower bound on the probability. So it's like probability minus some sort of an entropy term. This is all like stuff that is derived from physics, basically. So okay, so now I guess deep learning stuff. again, the book doesn't have a lot of things, so I added a few things from my own. But so here is the sort of the canonical graphical models that is often used in deep learning. People use things called deep belief nets, but most common one is restricted Boltzmann machines. So what is a restricted Boltzmann machine? A restricted Boltzmann machine is actually just a graphical model where let's assume that these are v1, v2, v3s. These are some sort of observable variables, right? So it could be whether, again, like, you know, some sort of whether I'm going to my commute is going to be shorter than something, or is it going to rain, etc., etc. They are connected to some of the hidden variables which you do not know or you never get to observe, right? So it's another way of expressing dependencies between v1, v2, and v3. And so instead of directly connecting v1 and v2 and v3, you connect them to some hidden variables, right? So this is why it's called a restricted Boltzmann machine. A standard Boltzmann machine is where you allow all sorts of connections between the nodes, right? And in fact, the funny thing is, like, when the whole deep learning thing kind of took off again in 2006 or 7, this was one of the hottest things that people were doing. Like Jeff Hinton was working very actively on this, and I guess it's not as popular these days anymore.
Does the graph need to be complete?
Typically it is, because we'll talk about some of the stylistic differences between, and I think Ian goes into a good detail, and that's I think one of my favorite sections in the book, where he goes into some details about what is the differences between the graphical models community and the deep learning community. The answer is, in graphical models, people try to impose semantics on these variables and the connections and the hidden nodes. What do each of them mean? Whereas in deep learning, you typically just care about prediction, right? So you start with some sort of an over-complete representation. So you connect everything to everything, and then you hope that you will discover it from the data. So a restricted Boltzmann machine is just a Markov random field where the distribution is factorizes over edges and nodes of the graph. So the probability of hidden units and visible units is actually given by the exponent of a linear function, right? So this is a function over x's, which is just a clique of size 1, right? And then this is a function over h, which is just a clique of size 1 as well. And then this is a function over x and h. So this is a clique of size 2, or an edge of size. I should maybe just drop the usage of the word clique, because it's not really, we're not cliquifying the whole thing. We're just assuming that the probability of x and h being in any state is just a function of linear terms and then pairwise terms, right? Or unary terms and binary terms. And then some sort of a normalization function. So these can be arbitrary variables, by the way. So you're assuming, since x and h is discrete, you don't have to assume anything about phi and phi I, phi j, right? Phi I, phi j are just explicitly described as, if x is 1, then phi I is, I don't know, minus 1,000. If x is 0, then phi I is 1,000,000, right? It could be anything. You don't really have to make any assumptions about phi as being continuous or anything like that.
Basically, the input is always categorical.
Typically, yeah, the inputs are discrete in this case. You could have instead of, let's say, discrete distribution, you can have maybe like a density over these h variables, but typically you just assume that they are. And for h, you actually don't really care if they're discrete, as long as it allows you to express the probability in a good way. Then you don't really care. So this is also called a harmonium, which is, I think, a funny name. So the beauty of this structure again is that, if you recall the Markov random field assumption, this node, or let's say this node, which is, let's assume that this is connected to all 3 of the hidden nodes. So this is the observed node. It's independent of all the other observed nodes given the hidden variables, right? So in some sense, you can sort of like do kind of like a forward prop and a back prop on this, but in a different sense, not for gradient descent, but you can, in other words, the probability of x, let's call this x2 being 1 or x2 being 0, is only dependent on the hidden nodes. It doesn't depend on any other x's. right? So the probability, so in other words, the probability of the entire x vector given h is a product of probability of each of the xi's given h, because they're all independent of each other, right? Once you've given h, you've given everything that they need, right? So often people do inference using like an iterative method. So you fix the h value to something, then given the h, you sample x, given the x, you resample h, and then you sort of repeat this process, right? Any questions about this? Okay, so the differences between graphical models and DL. So I think one of the biggest differences is semantics. Graphical models try to assign semantics to what each of the nodes mean, right? Whereas in deep learning, you kind of just typically care about the input layer and the output layer, and you don't really care so much about the hidden layer, right? So as long as it gives you the right prediction, you're happy with it, right? Another kind of difference is that often in deep learning, the intermediate variables are continuous, right? So you can sort of like do gradient descent on those things, right? Whereas in this, most of the variables often, or in many cases, they can be discrete descent. Although there are some very cool new papers that are actually trying to solve graphical models using deep learning techniques, because deep learning techniques, at least continuous optimization techniques, tend to be much faster than discrete optimization. Structure, so graphical models try to achieve sparse structure so that you can actually understand them and you can ascribe meaning to them, whereas in deep learning, you typically just do fully connected because you just mostly care about prediction. And inference-wise, graphical models, given that they are mostly sparse, often use combinatorial algorithms. So more like data structure, often it draws heavily from theoretical computer science literature. Whereas in deep learning, you typically use continuous methods, or you're very happy just sampling. Right? So in some sense, I guess graphical models, you place heavy emphasis on doing inference efficiently and correctly. But in deep learning, you don't have so much emphasis on that. So I mean, I can stop now because this is the book and we can have discussions on it, or I can talk about discriminative models, which I feel are more useful.
Really good, but I do have a few questions.
Sure.
On the stuff
Oh yeah. So let's do them first.
So there's one about the weak structure model, and specifically the person asking says that you said if A correlates to C, then chance for B to also correlate to B will decrease. Is this the type or should it be C?
Oh, which one? This one? Oh yeah, this is probably type. Again, not my slides. So I would fix it. If A correlates to C, then chance for C to also correlate to B will decrease, I guess. Yeah.
No, the chance for B to also
Correlate to C will.
Okay,
Yeah. I mean, it's so what the easiest way to think about this is, again, like a simple example. Let's say there is smog, and let's say there is rain, right? And now so A is smog, B is rain, and C is me being late for work by more than an hour, right? So if I know that I'm actually late, so let's say the smog and rain occur independently of each other. But if I know that I'm late by more than an hour, right, then they don't have to occur together, right? Each one of them can explain this. So the probability, in other words, the probability of one of them to actually necessarily hold true goes down if I know that the other one holds true. So if I know that there has already been rain, then that can sort of explain why am I late. So there doesn't really need to be smog for me to be late. So that's the explain away effect, right? One of the variables explains it, so the other variable doesn't have to. So they're kind of related to each other. They're not independent of each other.
I also have another question. So this one is about factor graphs, and specific to the book. So in the very beginning of that part of the chapter, it says, in undirected model, the scope of every phi function must be a subset of some place in the graph. Ambiguity arises because it's not clear if each place actually has a corresponding factor whose scope encompasses the entire flake. And the person asking is wondering, like, what is the entire flake that Ian is referring to?
So the entire, so typically, again, what happens is the theorem here is actually, I mean, so this is a slight bit of a theoretical claim, but sorry, let's go over this anyway. Let's see if I may have deleted that slide from this, but so here's the idea. Let's assume that I'm giving you a graph which has the local Markov property. So what local Markov property means is that, again, each node given its neighbors is independent of every other node, right? So I only tell you this, and now I ask you, write down the probability distribution over this graph, right? So there is a beautiful theorem called Hammersley-Clifford theorem that says that the probability distribution over this graph, given only the local Markov property, can actually be written as the product of probability over cliques of a graph that has been moralized, right? So by moralized, I mean, just basically what it means is that there are no cycles of length 4 that don't have any chord connecting them. So if or length, sorry, cycles of length more than 3 that don't have any chord connect. So triangles are okay, but if you have a graph like this, then you have to sort of connect them through a chord, right? So once you've done this moralization over the graph, and then you should find the cliques in the resulting graph, and the theorem states that the probability is a product of probability of each of those individual cliques in the resulting graph, right? So the issue is, in many cases, we don't really care about the cliques, right? So like, for example, if I gave you this graph and if I started moralizing it, you would end up with a complete graph. And I don't really want to express such a huge distribution. So I'm just going to make a simplifying assumption and say I want to assert that the probability is just sort of factorizes over the edges and the nodes and not any bigger factors, because the larger the size of the factor, the probability of expressing that grows exponentially with it, right? So if I gave you a clique of size m to express the probability of that clique, you need 2 to the m number of different entries in that conditional probability or in the probability table, right? So which is why, you know, factor graphs are useful, because now you say, you know, screw cliques, I don't really care. All I really care about is which of the 2 nodes interact with each other, right? Because at the end of the day, I just want to express the probability distribution as a product of some positive functions and then normalize them, right? Those positive functions could be over edges, could be over individual nodes. If the positive functions are over nodes, then it's kind of like a naive Bayes model where every variable is independent of each other, right? But if it's over edges, then it becomes slightly more interesting. It doesn't have to be over edges. It could be over like what is called a hypergraph, where you have subsets of nodes of size greater than 2. It could be over 3 nodes at the same time or 4 nodes at the same time, but that is just too big to express. So that's why you use factor graph. The original clique representation is theoretically justified, but it's not practically useful.
Got it.
Cool. Yeah.
Do you have some experience in practice with large? Did you see any large Bayesian networks in practice?
Not very large, honestly. I've seen. Well, actually, I've never worked with Bayesian. I've always worked with Markov random fields, because Bayesian networks it's very sort of more in the multivariate statistics kind of thing. In machine learning, typically you don't really care so much about causality as you just care about making predictions, right? So I have conditional random fields. I guess some of you may have used them. Conditional random fields are just a kind of Markov random fields. So in natural language processing, people use conditional random fields for named entity tagging, but none of those are very large. It may be of the size of the number of words in a typical document, so like 500 or 600 or 700.
I just saw latent delay allocation, and that seems like it's the only example I know that's for topic modeling.
Yeah. Right. So in latent directional allocation, it's a great example of a graphical model. They don't have so much. I mean, I guess they have very clever inference algorithms that allows them to sample topics, condition on words, and then some other sort of higher variable condition on topics, and they don't have to be discrete. So then if your variables don't have to be discrete, then you can get away with a lot of things, right? You can just use continuous optimization technique. You can do gradient descent, but you can't do gradient descent on a continuous on a discrete optimization domain, right? So that's why LDA graphs can be very large, but then they don't have some of the shortcomings some of these discrete graphs have.
As a model, that would be simple, like you just invariant or something.
Yeah. It's just a simple Bayesian plate, right? Yeah, they're great.
Anything more ugly.
Oh yeah. You should look at some of the I mean, I don't think ugly Bayesian networks is a good Google search, but there are these graphs from like some of the early days. There's a graph that I saw which was about some sort of a security or an alarm system, and that had like these. It had like 500 nodes. It was hand curated. It was just crazy. Whoever came up with that is doing the work of God, I guess. It's too much. Yeah.
Could you comment on how the structure can be learned through data? Structure potential.
Yeah. So let's say. So what is a let's assume that you're learning a Bayesian network, right? What you really want to do is learn whether there is a dependence between a variable and some other variable. Let's assume like you've broken down the whole thing. So okay, let me take a step back. Given a Bayesian network structure, I can learn the parameters for that structure using maximum likelihood estimation, given the data, right? So if I gave you the structure, you can learn the parameters with maximum likelihood. So
Parameters, you mean the nodes?
so no, so by parameter I mean the conditional probability table.
Okay.
Right. So what is so how do you actually, let's take another step back. How do you specify a Bayesian network? You specify this by you specify it by the structure plus the conditional probability table, right? So if I gave you the structure, you just have to learn the conditional probability table from data, right? You can learn that using just maximizing the likelihood and treating each of the probabilities as parameters, right? And that is a convex problem, so you can actually just like solve it exactly. So what people do is, or at least did in the early 90s, was that they would start with some structure, then fit the parameters, then they would add the nodes in a greedy way, actually add the edges in a greedy way, right? And they had the greedy optimization was maximizing some what is called an MDL objective, which is like minimum description length objective. So it was some combination of how much do I gain by adding this edge minus times the complexity of the graph that comes from it.
So there's a heuristic.
There is a heuristic. So it started off as a heuristic, but then people are using more cool techniques. Like now people are using what is called L1 regularization based optimization. So you could say if I want to predict the value of a node given all of the other nodes. So let's say I formulate a prediction problem that predict this node given every other node in the graph, everything, right? And then I put an L1 penalty on the connection strength between this node and all the other nodes. So those nodes that do not actually relate to this node, their value will become 0, right? Because that's the property of L1 regularization. L1 makes things 0 if it's not useful. So then you can use that to learn the sparsity structure of the graph. And then there are actually theorems that prove that this is sort of correct in some cases.
So you start with a simple representation of the model and then add edges. It's just not the other way around.
No. So depends. So you could do simple to that, and the other way, the second thing I described was, in some sense, you're training. Let's say you're training a logistic regression. I'm simplifying this a lot, but train a logistic regression to predict node x5 given all the other nodes. So x1 to x a billion, right? And you formulate this as an L1 optimization based prediction problem, right? And then you figure out that most of these values are 0, so none of the edges are present. L5 x5 only depends on, let's say, x2 and x10 and x1000. So then you connect those. So you kind of like assume that everything is connected, but then formulate it as an optimization problem and then find out that most of them are not connected.
And the amount of data needed to learn that model would be.
I don't know. I don't know the theorem there, but yeah, it's function of number of edges and nodes and something like that. But I mean, I can definitely point you to those papers.
But in that slide behind you, so you have the joint distribution equal to some product of some
Mhm.
parameters.
Mhm.
So you have 1, 2, 3, 4, 5, 6, 7, 8 parameters being multiplied.
Mhm. Yeah. So in total, you have only 36 parameters. Yeah, because each of those factors is a lookup from a table, right? And that table has a size something 8 to 4 something.
Yeah, instead of having 2 to the 8 different
Yes.
zones.
Right.
So you will have to obtain data for each realization of those 36 combinations.
Yeah. So you would have to get data for those.
Enough data to represent.
Yeah.
those
Yeah. So you would. Yeah. So that's a good point. Like if you're estimating conditional probabilities here, then you would have to have all of that data, which is still not that much, but yeah, still quite a bit. Yeah, it's like whatever, like n times the x 2 to the size of the largest, whatever, conditional table or something.
What's the best way to traverse for big graphical models to find inferences? Would it be a BFS, DFS, or just depend on the structure?
So is this inference or is it sampling? So sampling, yeah, sampling you could do with BFS. For inference, again, the inference question is there are different kinds of inferences. So you might want to say something like, what's the probability of x1 being something, or conditional probability questions like x1 being something given x2 and x3. People use, so if there are very nice theorems there. If the graph looks like a tree, then there is a linear time sort of algorithm which sort of looks like the Viterbi algorithm, but it's like a generalization of Viterbi that converges in linear time and gives you the right probability. But if the graph doesn't look like a tree, then you do what is called message passing algorithm, which is used for inference. And each round of that message passing algorithm takes the size of the order of edges, right? Takes that much amount of time. And you do like 4 or 5 or whatever number of rounds. It converges fairly quickly in practice. So you use, yeah, belief propagation or message passing for that. Yeah, there's a huge literature on that. Like I'm not even touching, like it's a tip of an iceberg. Yeah. Yes.
What do you think are the main applications for this?
So so there are 2 answers to this. One is are we talking about modeling the distribution over some set of variables? Is that the only problem, or you're talking about making predictions for some variables by modeling their interdependencies, but also given some sort of other variable x? So so the former, there are some applications in gene expression, like people often, especially like in biostatisticians, use this to express distributions and how different possible genes interact with each other. But I don't know of a lot of applications of purely modeling the distribution. It's used in density estimation and all of that kind of stuff. So that is part of like unsupervised learning. But in supervised learning, there's a huge number of applications. So then in supervised learning, this sort of becomes a subset of what is called structured prediction. So what a structured predictions algorithm problem is let's say I have given you a sentence and you have to come up with the syntactic parse of that sentence, right? So the input here is x, which is the words, right? And the syntactic parse is, let's say, y, and that is not just a 1-0 variable, right? It's sort of like a combinatorial variable, which is like a tree, right? So then you would predict that not as independent variables, but you would predict all of those n number of variables or the entire tree as just one single variable, right? So then that has a lot of applications. Like parsing is done this way. Part of speech tagging is done this way. In computer vision, people were doing again scene segmentations or even not object recognition so much, but I guess I'm not that familiar with the vision application, but even like 3D image identification and things like that, because it was very crucial to model the interactions between different output variables. So in the way I think about this is deep learning is extremely good at modeling the interactions between input variables. So if I gave you input x, which is like pixels or words or word embeddings or whatever, the deep learning can actually come up with higher and higher levels of abstraction that model how these x's interact and form higher and higher level of features, right? But what graphical models do is they model the interaction on the other side, which is on the output side, right? So for example, if you want to, I don't know, like predict that something is, this is a noun in a sentence, right? Then often a noun is not immediately preceded by, let's say, some sort of a verb, right? In English, at least. So then this is sort of an interaction between the output variables. And this is captured by graphical models or structured predictions, because then you can encode distributions, or what are the allowed distributions between these y variables. So it's sort of like a different side of the story. So it's used, to answer your question, long story short, it's used pretty heavily in NLP and vision, but in the more discriminative setting where you're predicting y given x, not simply to model the distribution over some x. Sound good? Question? More? So yeah, then let me talk about the discriminative setting. I mean, it's not like I did make these slides very carefully, but I might be even more sloppy there. But yeah, so this is what we call conditional random fields. They're related to Markov random fields, and they've been they've been pretty useful for the last 16 years. So people started, this was invented in 2001. So what you're doing here is you're predicting a bunch of variables, let's say a sequence of variables, y1, y2, y3, y4, whatever, up till yn, given some x, right? So and just like in Markov random fields, the probability of y given x is just some sort of a Gibbs distribution. A Gibbs distribution there's a distribution with this form, exponent of some variables, exponent of some function, right? So this is just like Markov random fields. The only difference here is that these the input feature vectors now also have x's in them. Previously, we were just modeling dependencies between the y variables or just the observed variables. Sorry, the variables that we are trying to predict. But now you also have to model the interactions between x and y, right? So this is super useful. Actually, in fact, I found this very cool set of slides. Let me present those. So now again, sort of taking a step back and talking more about on discriminative prediction. So typically in normal machine learning or whatever standard setup, you have an x, input x can be anything, could be images, sentences, whatever. And you want to predict either a real number or want to predict some category, cat, dog, whatever, right? But in structured output learning, input x can be any kind of objects, but the output here is also a complicated object. It's not just ones or zeros, right? So it can be, whether, I don't know, something like, how is this protein going to fold? So this is very commonly used in predicting protein folding because each of the amino acids in the proteins interact with each other. So that can be used, that information is used to predict how this protein is going to fold. Or what is the syntactic parts of this sentence, right? Or what is the segmentation of this image, right? So the output here is not clearly a 1-0 object, but it is described by some sort of a data structure, right? So this is what is called structured output learning. So examples are, let's say, semantic image segmentation, right? So you want to do background, foreground. So the output here as such belongs to a space of 2 to the, or not even 2 to the, but like 2 to the m times n, right? Because m is the width of the image, n is the height of the image, right? And input x here is just pixels. And another one is, let's say you have a human pose estimation problem, right? So we have k different body parts and they interact with each other. So you could predict, you could either choose to predict where each of the body part is independently of each other, but that doesn't make any sense because human body can only occur in a certain sort of different defined set of states. So it helps to model the interactions between where your hand is and where your arm is and where your other hand is and so on and so forth. So you don't predict one hand on this side and the other hand on that side. Often also people use this in natural language, bioinformatics, speech processing, robotics, etc., etc. And typically what you do is, normally you just had a feed forward function, right, where you feed in x and you at the end you get f of x, which is y, right? Here you do something different. You minimize an energy function of x and y together, right? So where y belongs to only the set of allowable configurations. So you don't allow certain configurations, you disallow certain ridiculous configurations, and for each given value of y, there is a certain energy associated with it, right? So y here could be, let's say there is one particular y. Let's say we're talking about human pose estimation, where you're predicting the arm is on this side and the leg is on that side, right? So that's an allowed, technically that's an allowed value of y, but you want the energy of that prediction to be low or to be very high, right? So high energy is bad, low energy is good. And then the configuration in which a y is on the arm is on this side and legs are on this side, you want the energy of that to be low, right? So this is typically how you formulate prediction problem, where you minimize certain energy function, right? And the goal of this energy function is that it captures interactions between x and y and between different parts of y and two other parts of y, right? So you want all of the parts of y to fit together nicely, but you also want to model the interaction between x's and y's. So this is what I found these slides and I sort of modified them a little bit, but again, so this is like a sort of like a standard example of not doing structured prediction, the regular prediction, in which you're given a convolution net, you run it on an image, you get something at the end, then you have a softmax or you have a multi-headed softmax, right? And you predict the probability of a cat being there or a cat's head, and etc., all sorts of stuff, right? So in other words, the probability of different things here is just a product of probabilities of each thing independently.
Sorry.
Yes.
Can you select the screen to be shared?
Oh, sorry, totally forgot to share. Oops. Yeah, I'm just trying to. Okay, does it sound good? Okay. Right, so in this case, you're not modeling any interactions between the y variables. So if you don't model the interactions, then you might as well just predict them independently, right? But you do want to model the interactions. So in that case, the probability of each configuration given x, which is the input, and w, which is the parameters, is given by some sort of a function of x and y together, right? Divided by some sort of a normalization constant, right? And the normalization, it's not a constant because it's actually a function of x at this time. So in original Markov random fields, z was a constant because you were just summing out everything. But in this case, z is going to be a function of x. You're just summing out all possible y's, right? So basically what you need here is just a scoring function, right? And it's pretty easy to see that this kind of way of making prediction generalizes the standard way of making binary prediction, right? Because you can always write the negative of the loss function as a scoring function, right? So then you would predict the variable that you would normally predict, right? So what I'm trying to say is like the scoring function based prediction is a general way of doing the standard sort of binary prediction. And inference is just described as maximize the score. So typically, again, so how do you do training in this? So you want to maximize W when you're given some tuning examples, X's and Y's, and you want to maximize the probability of Y given X, right? And so the algorithm here is fairly, it's a little bit complicated. So you do a forward pass to compute the scoring function, right? So you're given X's and Y's, and then you compute the marginal probability or the probability of each of the Y's given X. But then you do a backward pass. Once you have the probability, you do a backward pass to obtain the gradient. So the tricky part is obtaining P of Y given X is not easy because you have to marginalize, or you have to do a sum over all possible Y's, right? And the number of possible Y's can be exponential, right? So that's where people often use things like dynamic programming algorithms and stuff like that to compute that in an efficient way. So yeah, so again, the graphical models, we have already seen them. It's a convenient way of expressing dependencies between different variables. You can have the unary potential, which is just the let's say, think of it as a prior probability of just some one node at a time. Pairwise potential, which is the prior probability of two nodes interacting. And then you can have higher order potentials, which are connecting multiple different nodes. And let's, yeah, so the only tricky part here is basically, now you have X's, which are learned using, the variables are obtained using, the input to Y is obtained using some sort of a deep learning like algorithm, right? So let's assume there are raw pixels, then you have a convolutional net on top of it. That the output of that feeds into Y, where you predict the Y, right? So now, but during training time, you're given the Y and you're given the input pixels, right? And how do you train the parameters not only of how your Y's interact, but also the parameters of your convolutional net, right? And so this is a nice paper that sort of talks about doing this. I think it's maybe a little too complicated to discuss this now that we have almost an hour and a half into the talk. But anyway, this has been, and basically what the authors do is they show that it's important not only to model the X variables, but it's also important to model how the Y's interact. Because in other words, if you're not learning how Y's interact with each other, then you are actually putting too much burden on your deep learning model to learn all possible ways X's can interact and can affect Y, right? Or in other words, I think you're basically saying, learn a good parameterization, let's say for your conv net, that works well for all 2 to the n possible settings of your Y variables, by not actually explicitly modeling how Y's interact. Yeah, I think that's, well, there is a, I don't want to talk about this one, but this is basically what, this is a new work called Structured Prediction Energy Networks. And it takes a step further, and it says that I'm also going to model the interaction between X and Y, not as a combinatorial algorithm, or not as some sort of a dynamic programming algorithm, but I would replace that also by a neural net. So then I convert my Y variables into some sort of a continuous variables, and then I model everything as a neural net, end to end. You can train it using backprop, and then at inference time, I get some values for the Y variables, which are continuous values, but then I just round them either to 0 or to 1, and that's my output. Yep, that's it. Questions?
Will you be sharing the slides?
Sure, yeah, I will.
Awesome.
Cool.
If there's no more questions to the questions, then I know we have some people who want to make announcements.
Yeah, that's right.
Thank you so much.
I'm gonna. So I'm just going to.
This is totally a shameless plug. So I got the permission to Alina to pitch our company. Actually, it's just going to take a minute.